So we're done with the conic sections, right? And the next two sections, we skip 10.5, which is how to rotate the axis so you can actually have conic sections which are not horizontal and vertical. We're just skipping over that one. The next section after that is actually parametric equations and then polar coordinates. I'm going to do this one first because it'll probably take longer on this one than it will the other. We're going to take a quiz next class, so it leaves more time for a quiz. And neither one really, they're just kind of separate topics. One doesn't depend on the other anyways. So we're going to do polar coordinates first. And polar coordinates are a way to represent points in the plane which involves not x and y. And the example that I always give is actually not polar coordinates. It's actually spherical coordinates. So polar coordinates is what you would use if you are in a flat surface in the plane. Spherical coordinates is what you would use if you're in space, right? We did that already in chapter 11. And the example that I'll give is, when we forecast the weather, first we send up balloons all over the world, then we assign to evenly spaced grid points everywhere on this map, a value for all the variables that we're measuring, which is temperature and pressure and wind and humidity. All those kinds of things have to have a value at every point. And then we use math equations to model them. And those equations, in the mid-latitudes, at least where we are, kind of look like waves, right? It's the high pressures and low pressures that you see everywhere. Now, this Mercator projection, which you would use x and y to find any place, and you could pick an x, it'd be how much you're going left and right, and a y is how much you're going up and down. You could certainly do that. And when you initialize the model, because you're just starting out, it would be the case that at negative 180 longitude, right, you would expect that your model has the same value there as it does there at positive 180 because it's the same spot, right? So now we would run our computer models and it would take that sine wave and it would start to change a little bit. And what's going to happen is that end of the graph is not necessarily going to be the same as that end of the graph because in terms of our graph, they are different points. Even though they were initialized with the same data, they're going to start to diverge, right? They're not going to be the same. And that's a problem because this is in the middle of the Pacific Ocean. It's the same spot here as it is here. So instead of using what you call rectangular coordinates, x and y, to do this, we use spherical coordinates. In spherical coordinates, we're going to use, we use latitude and longitude, and then we've got the what we will call the r, the radius, is the distance from the center out. So the latitude will tell you where you are up and down. The longitude will tell you where you are this way, right? That could tell me that, for example, I'm right there in Italy, but it wouldn't tell me, like, am I at the surface? Am I at 20,000 feet? Am I at 40,000 feet where airplanes are flying? You need to know all three of those to locate one spot in space. So we need two angles and a distance from the center. Now, when we do that, because this is actually a globe, we're not going to have that same issue that at one spot it's starting to diverge because the domain, the background, it actually wraps around on itself. So if I draw a sine wave to start out, it is not, going to different solutions at the ends of the graph because there is no end of the graph, right? Just like we know when we, use the unit circle, every time you go around, you're repeating values anyways. You get the same thing. So this is an example in spherical coordinates. We're actually doing polar coordinates. We're not going to be doing it in space. We're just going to be doing it on a flat surface. So polar coordinates, it's another way to locate a point in the plane. We're still using the parentheses. This time it's not x, y. It's r comma theta. Right? R comma theta. Now, we haven't really used this term before, but the xy, which Cartesian coordinates, but they call them, in this section, they call them rectangular coordinates. And I think we could figure out why they're called rectangular coordinates. But so rectangular coordinates refers to x, y. Polar coordinates are theta. So they give it an example here, right? The r is what they're calling directed distance. It's the length of that, right? If I want to locate this point P in the plane, okay, first I need to know how far away is it from that point right there. Okay. Now, you probably think of r as radius. That's fine. I mean, here, that's the definition. R is directed distance, but you could think of it as radius. And then the angle, they're calling it directed angle, right? It's the angle with the x-axis. It's not necessarily positive. Like when we did direction angles in the last stuff we were doing, then that had to be a positive angle with a positive x-axis. Now it's not, right? Now it's just any angle with a positive x-axis. Josh, okay? Now, two things, kind of vocabulary words. I'm not sure if this is on the next slide. But this point right here is the origin, right? I think it is on the next slide. That is the origin. But when you're doing it in polar coordinates, that's called the pole. And this is the x-axis, right? But the x-axis in polar coordinates is called the polar axis. What's that? Directed distance says this. Everybody done? Okay. So the first thing we do is we plot points in the polar coordinate system. If you notice, and these are their three graphs. We'll do three others where we have to do it ourselves, but this is their graphs. That we're not using the rectangular grid anymore. We're using a concentric circle, right? Where the inner circle has a radius of 1, then we've got a radius of 2, then you could have a radius of 3, because that'll help us to locate, the distance from the pole that we are. So this first one, we're trying to plot the point 2. The radius is 2. The theta is pi over 3. So if the radius is 2, that means the point lies somewhere on the circle which has a radius of 2. If the angle is pi over 3, most of these, they are giving us in radian measure. I haven't seen that they use degrees at all in here. Just it's always radian measure. Referring to your unit circle, you should know where pi over 3 is, right? If pi over 3 was here. So it's along this line and on this circle, so that's the point right there. Pierce. Good. Try this one. Now we're doing 3 negative pi over 6. So if the r is 3, then it's going to be on this circle, which is a radius of 3 away from the pole. And if the angle is negative pi over 6, we know negative means go clockwise, and negative pi over 6 was here, right? So it has to be on this line and on this circle. There you go. And last, radius is 3. Oh, that's a mistake, isn't it? Isn't that what I just said on this one? I wonder if my picture is different. Oh, no. This is different. Now it's saying 3, 11 pi over 6. But remember when we dealt with angles that you have such a thing as coterminal angles. 11 pi over 6 as an angle would be in the same place. So whether you call it negative pi over 6 or 11 pi over 6, it's still saying the angle is on this line and the radius is still 3, so it's that point right there. Okay, so let's do a couple more. 3 more. Okay, so now we want the radius is 3 and the angle is pi over 4. Okay, which quadrant is it going to be in? First quadrant. And where is pi over 4? It's exactly in the middle, right? So it has to be exactly on this line. And it's a radius of 3, so it's there. Right, this angle right here, pi over 4. Okay, 2 negative pi over 3. Which quadrant is it going to be in if it's negative pi over 3? Fourth quadrant, right? Negative pi over 3 would be right about there, right? This is 1 pi over, pi over 6, pi over 3. So maybe it belongs there. I'm just estimating. And so there's negative pi over 3. And the radius is 2, so it's here. Get it? And the last one, 5 pi over 3, 2. What quadrant are you in at 5 pi over 3? 4, right? It's actually the same point we just graphed, right? They're doing the same thing they did in their examples before, which is 5 pi over 3 is still here. Remember, it's pi over 3, 2 pi over 3, 3 pi over 3, 4 pi over 3, 5 pi over 3, right? Now you're going as a positive angle, 5 pi over 3, but it's still along that line, and the radius is 2. So there's the point. What's that? I don't know, probably not. It's not going to take an hour. Okay, which points out that could that ever happen with x rectangular coordinates? Is there more than one way with xy coordinates to name one point in the plane? And the answer is no. It's unique. You know, if you have an xy address, that's one point in the plane, and there's no other way to name that point. Right? But when it comes to polar coordinates, because of coterminal angles, there is more than one way to address any point in the plane. You add or subtract 2 pi, and you're at the same place. And there's actually one more wrinkle in that we'll see when we do these next problems. It's not just about adding and subtracting 2 pi. But at the very least, this explains, addresses are not unique. There's more than one way to name a point. Okay. So the next kind of problem we do is then coming up with more than one way to represent the same point. So it says plot the point negative 3 pi over 4, and then find 3 additional polar representations for this point using theta in between negative 2 pi and positive 2 pi. So let's see, if I sketch a graph here, it's a radius of 3. The angle is negative 3 pi over 4. So where am I going to find that? Which quadrant? It's in the third quadrant, right? So it's somewhere down here. I'm not going to draw the concentric circles. I just say this is my negative 3 pi over 4. And this point is negative 3 pi over 4. Okay, so there's the point. How do I find my 3 representations? Well, let's see what they did here. The first of the 3, they added 2 pi. Okay, like we said, add 2 pi, that gives you 5 pi over 4. That's this angle going in a counterclockwise direction, right? 5 pi over 4. Now, could you subtract 2 pi? If I take negative 3 pi over 4 and I subtract 2 pi, right, now I'm going to have something that is less than negative 2 pi. So that wouldn't be in the interval. So I can't add and subtract. I can only do one. In this case, I could add. Since that was a negative angle, I could add and get one of my other representations. But note the last 2 here, right, how are they getting those? They're using negative radiuses. So a negative radius goes in the opposite direction. So what they're doing is they're saying, okay, if the negative 3 pi over 4 is here, then I could use pi over 4 as an angle, right, which is 180 degrees the other side. And then because the radius is negative, I'm not going to go off in that direction. I'm going to go in the opposite direction. So you use an angle which is 180 degrees the other side and a negative radius. So it's negative 3, and they've added, actually this is the one I just talked about. They've added pi to get an angle of pi over 4. So with a negative radius, angle is pi over 4, that means go backwards. And then you could subtract pi. Negative 3 pi over 4 minus pi is negative 7 pi over 4. Right? Negative 7 pi over 4 is like this, all the way around it there, and then backwards. Right, so sometimes they say between negative 2 pi and 2 pi. Sometimes it's like between 0 and 2 pi, something like that. So you just have to see what they're asking for. So let's see what we got. So we'll do the same thing with this. And we don't even have to graph. Well, we can just for the enlightenment. Okay, let's see. 3, 4 pi over 3. Which quadrant is it in? Right, 4 pi over 3, right there. Right, so it'd be about right there, and I'm just going to label it 3. I'm not going to put the concentric circles. 4 pi over 3. Okay, now we need to come up with 3 different representations for that. Okay, let's see. The first one, we can keep a positive radius, right? That would be 3 And what would I do? Add or subtract 2 pi? Yeah, it's already positive, right? If I added 2 pi, it wouldn't be between negative 2 pi and 2 pi. So I'm going to subtract 2 pi, right? So what is 4 pi over 3 minus 2 pi? Well, that would be minus 6 pi over 3, which is negative 2 pi over 3, which is like go this way. Negative, go negative 2 pi over 3. Okay, now second and third. Right, now we know we're going to be using a negative radius, and we're going to be using an angle which is opposite. So how am I going to find this angle here? You know what that angle is. The first angle, right? It's pi over 3, right? What would be 180 degrees the other side of that? Pi over 3. So there's 1. So let's see, we started with 4 pi over 3. It looks like we subtracted, what should I do to get the next one? I mean, if I started at 4 pi over 3 and I added pi, to get halfway around the circle, that would be too big. So I've already got that. How about if we just subtract 2 pi again? Right? Take this pi over 3 and subtract 2 pi. Minus 5 pi over 3. Right? That would be going around this way to find the same angle and using a negative radius. Okay, negative 5 pi over 6, which quadrant? It would be here, right? About right there. Right? And the radius is 2. So that's 2 negative 5 pi over 6. Okay, 1, 2, 3. Right? So we know it's going to go like this. 2, negative 2, negative 2. Right? How am I going to find the angle that goes here with positive 2? Add 2 pi, right? That's already a negative number, right? So when I add 2 pi, it'll be less than 2 pi. Negative 5 pi over 6 plus 12 pi over 6, which is 7 pi over 6. Okay, now with the negative 2, right, we want to say the angle which should be exactly opposite of it. And you should be able to say that angle quickly, pi over 6, right? If that's negative 5 pi over 6 or 7 pi over 6, and exactly opposite of that would be pi over 6, right? And how would you name that angle if it's with a negative, right? If I went around this way, it would be negative 11 pi over 6. And the last, oops, that was wrong. The last one. 3 pi over 4, where's that? 3 pi over 4 is there, right? 3 pi over 4. But the radius is negative, which means what? Where's our point? Which quadrant? It's actually down here. 3 pi over 4. It's actually down here. So it's negative 1, 3 pi over 4. Right? Because you're going the opposite direction with a negative radius. Right? Here's our 3 alternates. Okay, so the first one will have the same, negative 1, And then how could I name that as a negative angle? Let me just say, what is it? It's going in a negative direction. It's negative pi over 2, negative pi. Five pi over 4, right? I mean, if this is 5 pi over 4, then this is negative 5 pi over 4. Right? Now, the next two should have a radius of 1, right? But where are you going to find that angle? Exactly opposite. So what is this angle right there? From here to here, it's opposite of 3 pi over 4, negative pi over 4. And then what if I named that angle by going around that way? 7 pi over 4. You know, if you don't see it, you can add, subtract 2 pi, pi, all that stuff. But we do know how to name these angles just by going in a positive or a negative direction. Okay, so that's the second kind of problem. All right, the last thing that we do is we convert points and equations from polar to rectangular and rectangular to polar. And if you look at the picture, right, which is labeled here, and it shows for any particular point, which could be labeled with an xy or with an r theta, right? We know what all of those represent in the graph, right? X is this distance, y is this distance, r is the hypotenuse of that right triangle, theta is this angle. So if you can set up all of that, then you can come up with these equations to convert easily enough. Right? We would know that the sine of theta is opposite over hypotenuse. So the sine of theta is y over r, y equals r sine theta. Right? In the same way, x equals r cosine theta. Right? The tangent would be opposite over over adjacent, y over x. So the tangent of theta is y over x. And then Pythagorean theorem would tell you that x squared plus y squared equals r squared. So this is everything that we're going to use now to convert from one to the other, points and equations. Okay, so points. Convert from polar to rectangular. Okay, so what we need are x, y. We've been given the r and the theta. Right, go back to that. Which equations are we going to use? These here, right? If you want to know x, plug in r and theta into that formula. If you want to know y, plug in r and theta. So x equals r cosine theta equals the square root of 3 times the cosine of pi over 6 equals the square root of 3 times, what is the cosine of pi over 6? Not a calculator issue, this is a unit circle. Square root of 3 over 2, right? Remember the unit circle, right? Pi over 6 is right there. The x-coordinate is definitely more than the y, so it's root 3 over 2, comma, 1/2. That's what you're plugging in. So this is times root 3 over 2, which is 3/2. Right? Y equals r sine theta, which is root 3 times the sine of pi over 6, which is root 3 times 1/2, which is the square root of 3 over 2. So there's your xy is 3/2 root 3 over 2. Good, Courtney? All right, then we'll go the other direction. Right? If you want to convert something in rectangular coordinates to polar, so let's see. Let's sketch these points. So we're trying to find that point right there, and we need to know an r and a theta. How are we going to find the r? Yeah, I mean, if even without the formula, you're just going to use quadratic formula. Pythagorean theorem. The square root of -1 squared plus 1 squared. R squared equals x squared plus y squared. R squared equals -1 squared plus 1 squared. R squared equals 2. R is the square root of 2. Okay, then we need to know the angle. How would we find the angle? I mean, this one you should know anyways what it is, but you won't always. I mean, this is rectangular to polar, so we just use this one. We just use this one to find the r. Going to use that one. Tan theta equals the y over the x. Kind of like we found the direction angle with vectors. Right? So now we're going to go theta equals tan inverse of y over x. Theta equals tan inverse of 1 over -1. You know, if you put it in the calculator with degrees, let's say, it would give you an answer down here, right? Because that's where it's going to find a negative tan angle. Now, is that really where we want it? No, we know that it's going to be up there. I mean, in the end, it would be giving you a degrees there, but you know, because this is the same on each side, we know that this is going to be like pi over 4, right? This is pi over 4. It's half of pi over 2. So we have to name it by doing that kind of thing. So what would be that angle? 3 pi over 4. Theta equals, you know, if you said negative pi over 4, you know, then that would be taking you down here. But you know that your point is up there. So you would want to add pi to get 3 pi over 4. Or what else could you do? Make the r negative, right? You could definitely use this as the angle and then just make the r go backwards and still get you to that point. That's probably not what you want to do. So plus pi. Right, remember, we don't have, with direction angles, they said we had to give a positive angle. But this is not what they say with this. It could be any angle. It could be negative. No problem with that. So this r theta, right, r theta equals the square root of 2, comma, 3 pi over 4. At least one of the homework problems, you know, it's not going to be some unit circle value. You're going to have to just put it in the calculator. Now, convert to polar coordinates. Somewhat of a special case, but it's kind of like that one we had on the test, where it said find the direction angle of the vector. And because it was dividing by 0, people said there is none, instead of plotting it and just seeing that actually it was 270. In this case, convert 0, 2 to polar coordinates. So this is an x and a y. So graph it. Right? 0, 2 is here. So what would be the r and the theta for that? What is this distance? 2, right? R equals 2. And what is this angle? Pi over 2. Right? You wouldn't need a formula for that. You should be able to just graph it and say what those are. R theta equals 2 comma pi over 2. Now, I don't think that they've put it in here, but in none of these examples have we seen this. But for example, when you're doing this, going from polar to rectangular coordinates, it doesn't have to be something with a pi in it. You still assume that it's radians. There's some of the homework problems that are giving you decimal values, right? So you just have to, in the coordinate plane, try to understand that, you know, if 0 is here and pi, 3.14 is there, then half of that is there, 1.57, 3.71, you know, and just use that to place yourself in there if it's not given in pi, in terms of pi. Okay. So when you do equations from rectangular to polar, they actually don't even have an example for rectangular to polar because they just say you're going to do the same thing every time here. Right? If you've got x's and y's and you want to go to r's and thetas, then you're going to substitute r sine theta and r cosine theta. You know, so they give this above the example and kind of dismiss it as something that is obvious and doesn't really need so much explanation. But I'll just showing this kind of like it's their example. Right? If you have y equals x squared, which we know is a parabola, vertex at the origin, opening up. Substitute for y, r sine theta. Substitute for x, r cosine theta, but it's squared. So now you've got r squared cosine squared. And if you can notice, let me write it like this. R sine theta equals r squared cosine squared theta. And what have they done from here to here? They cancel as an r. Now, are you allowed to cancel an r? It's like divide both sides by r. I mean, why wouldn't you be able to divide by r? Because it'd be 0, right? But radius is going to be positive. So, I mean, if it had a 0 radius, what point is it? It's the pole, the origin, right? It had a 0 radius. So now notice what they did there. They solved for r. You know, once they got to this point, they canceled this r with that r. They solved for r. They divided by the sine. And 1 over the sine, oh, they really messed this up. So this is, oh no, this is what, because the r is over here, they had to divide by the cosine squared. So it looked like this. R squared equals sine theta, that's wrong, edit, undo. Divide by the cosine squared. And you can see they split that up, right, between sine over cosine and 1 over cosine. Right, that's where they got these Most of the time they solve for R. They leave it in a way that they've solved for R, but not always. You should recognize your answer in the back. Okay, the more interesting is trying to go from polar equations to rectangular equations. Okay, and I'm giving you specific examples that are like the homework problem. So you should just go to the examples to look. Because you wouldn't, if you've never done this before, some of these things we're going to do, you wouldn't even think of, right? But once you've seen them, then you say, okay, I know how to do that. Like this R equals 2. Right? We need to make a substitution that converts it from R's and thetas to X's and Y's. So which one of these would take R and convert it to X's and Y's? Right there, right? The thing is, you need it to be R squared. And if you have R squared, then you can substitute X squared plus Y squared. So we're going to go back to this. And if R equals 2, then R squared equals 4. And R squared is X squared plus Y squared. Which means what kind of shape is it? Say again? It's a circle, right? So got coefficients are equal, 1x squared, 1y squared. What does the 4 represent? R squared, the radius squared. So when you see it like this is saying the set of all points that have a radius of 2, which is kind of the definition of a circle. And that's what it looks like in rectangular coordinates. So you got to think of that. If they give you just R, you're going to square it and substitute X squared plus Y squared. Okay? Theta equals pi over 3. Okay? In the first one, it was the radius was constant. Now, it's the angle that's constant. So where's pi over 3? It's quadrant 1, right? But again, we could say you could have, as long as that angle is pi over 3, then it's the set of all points that have a radius, a theta of pi over 3. Now, if it has a positive radius, that'll give you all these points here. If it has a negative radius, it'll give you all these points here. So having the angle be constant is actually giving you a straight line that goes to the origin. Right? That's what it is. Now, how do we turn that into the rectangular coordinates for a straight line? Well, which is the only one that plugging in the angle, you get X and Y. Tan theta equals Y over X. Okay, so we're going to use that. Tan theta equals Y over X. And tan theta now is tangent of pi over 3 equals Y over X. But tan of pi over 3, go back to unit circle, right? Pi over 3 is there. That is coordinates of 1/2 root 3 over 2. Tangent is the y divided by the x, which is square root of 3. So this is the square root of 3 equals y over x, which means y equals the square root of 3 times x. Right, that's linear. It has a slope of the square root of 3. It has a y-intercept of 0. We're good. Okay, and then this one. Now we got r's and thetas involved. Okay, we have a secant in there. Do we have a substitution for the secant? I mean, we've got for sines and cosines. We don't have for secant. So somehow or other, this is going to have to turn into a sine or a cosine. Right, so let's see. First step, what if I just substitute? A secant is 1 over the cosine. Okay, that's okay, but what is the substitution that I've got that involves cosine, x and cosine? It's actually that x equals r cosine theta. How can I make an r cosine theta out of that? Multiply by cosine theta, right? If you multiply by cosine theta, now you've got r cosine theta equals 1. And you have a substitution for that. R cosine theta is x. So r cosine theta is a vertical line, right? It's x equals 1. Right. I'm going to show one more example because it's one. They don't have an example of it, but it's like the very first homework in that section of problems. It's the first one, and you would probably never get past it. And that is this. Okay. R equals 2 cosine theta, converted to rectangular form. So can we substitute, because there's an r on this side and a cosine on that side, can I substitute x? What do I need in order to substitute the x? What's that? You need to have an r times cosine of theta. You don't have that now, right? So how could I have an r cosine theta? Could I divide by cosine? No. Could I divide by r? So what could I do? Say again? No. You're close. Multiply is correct, but not by 2 cosine. By r, right? What will happen if you multiply by r? On the left, you'll get r squared. You got a substitution for that. On the right, you'll have r cosine theta. You have a substitution for that, right? So multiply times r first, right? Then multiply everything by r. Then you get r squared equals 2r cosine theta, right? And then this is x squared plus y squared. And this is x equals 2x. Now, do you recognize the shape? Say again? It is a circle, right? Is it in a standard form for us? No, and you're not going to be asked to do that, at least not here. Maybe on a test. But if I subtract the 2x to the other side, right, I'll get x squared minus 2x plus y squared equals 0. I would complete the square by adding 1 and adding 1. And now I've got x minus 1 squared plus y squared equals 1. So now that's standard form of a circle. Right? It has a center at 1, 0, and a radius of 1. Is it good? Courtney? Okay. So that's it. There's a lot of homework problems, so most of them are kind of basic. You know, I mean, when you just first learn a new thing, there's a lot of, graph the point, graph the point, graph the point. Make multiple representations. Convert points from rectangular to polar, polar to rectangular. Equations.